Alright, silly people, here's the situation. We have a circular wire with a current of I naught and a radius of A fixed in the XY plane, uh, and we are going to calculate the electric and magnetic fields in the far zone due to this loop of current without making any approximations of the like Hankel functions or the spherical Bessel functions. So we're just doing the entire um, vector potential expansion, uh, which is a little bit of a pain. So first of all, let's actually define the um, current density. So that's going to look like it's fixed in the xy plane, so the current's always going in the phi hat direction. And then you'll have an I naught, and it has to be a density, so it's gonna end up being divided by R, and then multiplied by a couple of Dirac deltas. Uh, R minus A to fix it in the circle of radius A, and then a delta function R minus, not R, it's just delta cosine theta, um, which is the same as writing delta theta minus pi halves. We're just trying to keep um, the loop fixed in the xy plane. That's all that Dirac delta is doing. But yeah, that's the current density. Um, then the multipole constant will be given by this integral d3 r prime uh, phi hat prime I naught, and this is supposed to be prime as well, or r prime delta r prime minus a delta cosine theta prime, and then the spherical Bessel function and the spherical harmonic. We'll split this up into angular and radial parts. So there's going to be an integral over phi from 0 to 2 pi of just all of this junk. So, oof. Phi hat prime is a function of phi, but I'm not going to tell you what it is yet. Um, but then in the theta integral, uh, we're going to end up having a d cosine theta prime ylm star theta prime phi prime, and then the Kronecker delta, or not the Kronecker delta, the Dirac delta, and then the radial integral we multiply by r squared, so it ends up just being r prime I naught delta r prime minus a. Okay. Um, so we actually have to expand the phi hat prime into Cartesian coordinates uh, because it's minus sine phi prime x hat plus cosine phi prime y hat, and then x hat and y hat won't change when we take the integral of them. So that's a useful thing to do. Um, the theta integral, we can go ahead and evaluate it because it's just a Dirac delta. Um, it ends up fixing theta at pi halves, like I said before. Uh, so this is just going to say y star lm pi halves phi prime instead. And then we can also go ahead and calculate the r integral because it is also just a delta function. So that's going to be a times I naught. That's it. No, that's not it actually, because I forgot there's a spherical Bessel function here. So it's going to be I naught j l omega a. All right. Yeah. So those are some really tough integrals actually. So I am going to have to expand the spherical harmonic, but don't be too scared yet. So the expansion of the spherical harmonic is going to look like 2l plus 1 over 4 pi l minus m over factorial over l plus m factorial, because I'm going to end up splitting up the d phi integral into a couple of different integrals. We're going to have one which is proportional to minus x hat, and it's going to be the integral of sine phi prime e to the minus I m phi, right? I wrote it down as just e to the I m phi prime d phi prime, right? And then also a plus y hat integral of cosine phi prime e to the I m phi prime, and that's being evaluated from 0 to pi, 2 pi, and also somewhere in there I need to multiply by the L m of 0 associated Legendre polynomial. And so let's talk about these integrals. That one is just going to be, and also this integral. Both of these are 0 if m is not equal to plus or minus 1. So m has to be plus or minus 1 for those integrals to actually exist. And if they are plus or minus 1, then this one is going to be equal to the sine, oh my god, that's an ellipse, the sine of m times I pi. While this one is just going to be equal to pi if m is equal to plus or minus 1. Okay. So that effectively fixes m to plus or minus 1. Okay. So I'm going to continue to write out this vector constant as being equal to I naught JL omega A square root 2L plus 1 over 4 pi L minus M factorial over L plus M factorial, which is going to be minus x hat sine of m times I pi plus pi y hat. All right, those are all of our integrals are done, and also multiplied by the associated spherical harmonic, or associated Legendre polynomial, I mean. So I am going to recombine now the spherical harmonics, just because. So let's actually just do setting m equal to 1. We have A I naught JL omega A. We'll actually have I x hat plus y hat times the YL1 of pi halves and 0 times the overall factor of pi because of the stuff inside the xy stuff. And then the AL minus 1 will be minus pi A I naught JL omega A minus I x hat plus y hat YL1 pi halves and 0, where I've made use of the fact that YL minus m of phi equals 0 is just equal to YLM phi equals 0 times minus 1 to the m. Right? So, okay, this is what we've got. So now we can actually look back at our vector potential, which is going to be a of r and t. So it's minus I omega e to the minus I omega t sum over L HL 1 omega r times the constant, so I naught pi JL omega A. I'm just collecting all the terms that they share. They both have a YL1, pi halves, and 0. And we have to sum over the m's, and then there's another spherical harmonic that we have to deal with. So we're going to have m equals 1 term, where we have the spherical harmonic of theta and phi, times the I x hat plus y hat stuff, and also a m equals minus 1 term, minus L minus 1 minus x hat plus y hat. And then, yeah, that should be good. So regrouping all of this stuff, we're going to pull out an I pi omega. There's a factor of a that I dropped, so I was just going to put it there. A JL of omega A, I naught, and I don't know why I'm putting the JL outside the sum. I'll just put the I naught there. And then the sum HL1 omega R, JL omega A, YL1 pi halves 0. And in the brackets, I'm going to group together the stuff which depends on I x hat and I n just y hat, because I'm going to end up turning these into spherical vector spherical harmonics. So I have that it's YL1 plus YL minus 1 plus y hat times YL1 minus YL minus 1. Okay. How am I going to turn these into vector spherical harmonics? This is a pretty silly thing to be doing, if I'm honest. But vector spherical harmonics are defined like this, where L hat is the angular momentum operator. So if we want the x component of the L0 spherical harmonic, it'll be the x component of the angular momentum operator times YL0, right? Similarly for the z and y components. But the z component is going to end up being 0. So don't worry too much about that. This is looking a little bit more like a quantum mechanics problem now, actually. We can split up the angular momentum operators like this into raising and lowering operators. These are just going to change the values of m. So we have that this is going to be 1/2, or let me specify, XL0x equals 1/2 of YL1 plus YL minus 1. And then XL0y is going to end up being 1/2, 1/2I, YL1 minus YL minus 1. And now you see why I actually wanted to group them together like this. Because now when we look back at our vector potential, minus I pi omega A, I naught sum over L, HL1 omega R, JL omega A, YL1 pi over 2, 0. We have an I times 2 times, so a 2I x hat XL0x plus 2I y hat times x y L0. So we can bring out an overall factor of 2 and an overall factor of I. That makes it a positive, so 2 pi omega a I naught. And then all of the sum terms, yl1 pi 2 0. And then this is going to be just, no, it's just going to be the vector spherical harmonic xl0, and that's it. So we have the vector potential now in the simplest form that it's going to get. In the far zone, well, I mean, in anywhere, the magnetic field will be the curl of the vector potential, but in the far zone, we pretty much just care about the radial component, so n hat cross del A del R, pretty much. So we'll just take the R derivative of that and the cross product of n with it. So I'm just going to say 2 pi omega a I naught sum over L. The only R thing in here is the Hankel function right there. So del R JL omega a YL1 pi or 2 0, and then this is n hat cross x L0 now. And then if you want, you can also get the electric field, which is typically just the magnetic field crossed with n hat, and that's certainly the case here. And I'm just going to copy all this junk down, cross it with n hat solid. Then the question also asks, what is the lowest non-vanishing multipole in the near zone? So I'm going to grab my expression for the vector potential because, again, this was gotten without taking any approximations to the size of omega a. But then I'm going to actually apply approximations to it. But clearly the lowest non-vanishing multipole is just the L equals 1, M equals 0 term, because x00 is just 0. So don't even worry about that. So just get the L equals 1 stuff. In the near zone, you can approximate Hankel functions as being on the order of minus I over omega r to the L plus 1 times 2L minus 1 double factorial. For us, we just need the lowest order thing, so that's going to be approximately minus I over omega r squared, and then 2 minus 1 is 1, so we'll leave it like that. And then there's also the near zone approximation for the spherical Bessel function, which goes like omega a to the L over 2L plus 1 double factorial. So for us, we have J1 of omega a is going to look like omega a over 3. Okay. And so let's put that all into our vector potential. 2 pi omega a I naught. We'll have minus I over omega r squared. This is a near zone approximation. Times omega a over 3. The spherical harmonic YL1 of pi halves and 0, or now it's just going to be Y11. So I just wrote down what y11 was. It ended up being 3 over 8 pi p11, 0. And then the spherical harmonic y10, or x10. So I'm going to go ahead and cancel stuff out. There will be no factors of omega after we're done. And we'll leave it like that for now. 2 minus 2 pi I naught a squared all over 3 r squared square root 3 over 8 pi. P110 is just minus 1. And then x10 is root 3 over 8 pi times this IE, or I theta hat. My handwriting's terrible. I theta hat minus cosine theta phi hat all multiplied by e to the I phi. Now when you square these radicals, these 3 is going to cancel out this 3. You end up with a total 8 pi on the bottom, and those pi's will cancel out this pi. So you just end up with a 1/4 on the bottom, and then, yeah, so you get positive I naught a squared over 4r squared times I e to the I phi, and then the stuff inside the vector. That's going to be your vector potential in the lowest non-vanishing multipole in the near zone.